This is how diamonds are extracted from different rocks in a deep, dark mine with millions of dollars invested and heavy machinery running around the clock. But could you do the same on a smaller scale? Because diamonds might actually exist in your region right now. And as hard as that is to believe, it's genuinely possible. The thing is, to not let a rare opportunity like this slip right through your hands, you need to know which rocks to look for. And that's exactly what this video is about. Most people have no idea that the ground beneath their feet could be hiding something worth thousands of dollars. They walk past the right rocks every day without a second glance because nothing about those rocks screams valuable. And that's the whole point. Diamonds don't announce themselves. They sit inside specific geological environments, carried upward by very particular rocks through processes that happened millions of years ago. Once you understand those processes, you stop looking at the landscape the same way. The Crater of Diamonds State Park in Murfreesboro, Arkansas, is a public park where anyone can walk in, spend the day searching, and keep whatever they find. Since it opened, ordinary visitors, tourists, families on vacation, people with zero geology training have found tens of thousands of diamonds. The largest diamond ever found in the United States, a 40-carat stone called the Uncle Sam diamond, came from that exact spot. These people didn't have professional equipment. They had one thing. They knew what kind of rock they were standing on. That's what today's video is going to give you. Not just the name of one rock, but a complete picture of every geological environment where diamonds occur, what each one looks like in the field, why diamonds end up there, what to search for on the surface, and what a raw diamond actually looks like when you find one. By the end, you're going to see terrain differently. And the last rock environment we'll cover is by far the most accessible one for anyone who wants to start searching right now, because it requires no special equipment and no mine access whatsoever, just knowledge and the patience to use it. Diamonds form roughly 100 miles underground in a region called the mantle, where temperatures hover around 2,000 degrees Fahrenheit and pressure is so extreme that it forces carbon atoms into the densest, most organized crystal structure found in nature. That process takes billions of years. The result is the hardest natural material on Earth, not because of what it's made of, but because of the conditions that shaped it. Carbon by itself is ordinary. Under that pressure for that long, it becomes something else entirely. Forming that deep is only part of the story. For a diamond to reach human hands, it needs a ride upward, and that ride comes from one of the most violent geological events in Earth's history. A specific type of volcanic eruption, one that no longer occurs today, created channels that punched straight through the crust at extraordinary speed. The key word there is speed. Normal volcanic eruptions are slow enough that diamonds dragged upward would be converted back into graphite by the heat. These eruptions were fast enough to skip that conversion, carrying diamonds intact from the mantle all the way to within reach of the surface. The material those eruptions produced is called kimberlite, and the underground structures they carved out are called kimberlite pipes. In cross-section, a kimberlite pipe looks like a giant carrot buried point down, wide and funnel-shaped near the surface, narrowing as it descends into the earth. At the top, where the eruption vented, it can spread across hundreds of acres. These pipes extend thousands of feet straight down, and the diamond content is not evenly distributed. The upper weathered section tends to have lower grade material, while richer zones can appear deeper. Commercial mines dig down through sequential grades, processing enormous volumes of rock to recover relatively small amounts of gem-quality stones. Not every kimberlite pipe contains useful diamonds. Some are essentially barren. Some carry only industrial-grade material. But the geological signature is the same across all of them. which means learning to recognize kimberlite gives you access to the same logic that diamond exploration companies use, scaled down, without the drilling rigs and the laboratory analyses, but based on the same underlying science. Once those ancient eruptions stopped and the kimberlite cooled, erosion took over. Rain and river water have been breaking down kimberlite at the surface for millions of years, freeing the minerals inside it and scattering them across the surrounding landscape. Diamonds, being virtually indestructible and extraordinarily dense, don't break down as they travel. They get picked up by streams, carried downstream, and eventually deposited wherever the water slows enough to drop its heaviest load. This process created the second major category of diamond environments, the alluvial deposits, where diamonds concentrate in river gravels and creek sediments far from any original pipe. We'll get into those in detail shortly. Kimberlite in its fresh form is dark bluish-gray to dark blue-green, dense and fine-grained. It doesn't sparkle, it doesn't look special. When it weathers down to the surface, which is what you'll encounter in terrain that's been exposed for long geological periods, it transforms into a yellowish, ochre-colored material that crumbles easily and feels almost clay-like. Geologists call this surface-weathered material yellow ground. Beneath it, the fresher, harder rock is called blue ground. Both can contain diamonds, though blue ground tends to have better yield in industrial operations. For a field prospector, the yellow ground is usually the accessible layer, and it's produced the vast majority of diamonds found by ordinary people at public sites like the Arkansas Park. There are 4 distinct geological settings where diamonds occur, and understanding each one's character, what it looks like, why diamonds end up there, what surrounds it, is what separates productive field prospecting from random wandering. Kimberlite is the foundation of everything. In fresh exposures, it's dark gray to dark blue-green, compact and fine-grained. What sets it apart visually from other dark rocks is the minerals it carries. Olivine appears as small, pale yellowish-green crystals that feel slightly soapy or greasy on fresh surfaces, a texture distinctive enough that once you've felt it on a known sample, you recognize it again. Pyrope garnet shows up as small, vivid reddish-orange grains, denser than anything else of similar size in the surrounding rock. Ilmenite appears as dark gray to black metallic grains. These 3 together are kimberlite's calling card. In the United States, confirmed kimberlite pipes exist in several states. Colorado and Wyoming have the most documented occurrences, with dozens of pipes identified in the Colorado-Wyoming State Line District, a zone running roughly along the border between the 2 states, where kimberlite eruptions clustered millions of years ago. Most of these pipes carry diamonds in quantities too low for commercial mining, but that doesn't make them irrelevant to a field prospector. The indicator minerals they shed into surrounding drainages are real and detectable with basic equipment. Kansas and Nebraska also have documented kimberlite pipes, as do parts of Michigan and the broader Great Lakes region. The existence of these pipes confirms that the geological conditions for diamond transport have operated on American soil in multiple locations. What varies is whether any specific pipe was rich enough to produce gem-quality stones in recoverable concentrations, and that question is separate from whether indicator minerals derived from those pipes can be found in accessible alluvial terrain downstream. The surface signature of a kimberlite pipe is subtle but learnable. Because kimberlite weathers differently from surrounding granite or metamorphic rocks, it often creates a slight circular depression or a low mound, depending on whether the pipe material is softer or harder than the surrounding country rock. Soil color in these areas can differ, slightly more yellowish or orange-brown compared to the gray or tan of surrounding terrain. Vegetation sometimes responds to the different mineral chemistry, producing a circular patch where plant density or color differs from adjacent areas. None of these features are dramatic or obvious, but they're real, and they've been used by exploration geologists to identify new pipes before any drilling begins.
In areas where kimberlite is known to occur, learning to read subtle topographic and soil color anomalies from a ridge or a high vantage point overlooking the landscape is a legitimate prospecting technique that costs nothing to apply.
Lamproite is the second major host rock for diamonds, and it's the one that produced the most publicly accessible diamond deposit in the world. Related to kimberlite in deep volcanic origin, lamproite has a lighter color, grayish to pale pinkish, sometimes with a slight greenish tone on fresh surfaces, and a somewhat waxy or dull luster. It tends to be less coarse-grained than kimberlite and can almost look like a fine-grained granite at first glance. The Prairie Creek Lamproite Pipe in Murfreesboro, Arkansas is now the famous Crater of Diamonds State Park. The pipe has been weathering for tens of millions of years, and the diamonds that were once locked inside the rock have gradually migrated toward the surface as the host material eroded. The Park Service plows the surface regularly to expose fresh material, and visitors simply walk across the field and look. The diamonds found there range from a fraction of a carat to multiple carats, and they come in several natural colors: white, yellow, and brown being most common, with occasional rare stones showing natural pink or green. What the Arkansas example proves in practical terms is that lamproite, and by extension kimberlite, once weathered, concentrates diamonds close enough to the surface that no machinery is required to find them. Surface searching in the right geological context is not a compromise compared to deep mining. It's simply a different phase of the same geology. Other lamproite occurrences have been documented in Montana, and geological surveys of the southeastern United States have identified lamproite-related intrusions in several other states. The overall picture across the country is of a craton that has seen multiple episodes of deep volcanic activity at various times and in various locations, with varying levels of diamond content, most of it unexplored at the level that would answer the question of whether smaller-scale prospecting is viable in any specific area. Alluvial environments are where most amateur prospectors find genuine success. When any diamond-bearing primary rock, kimberlite, lamproite, or eclogite, erodes over millions of years, the diamonds it contains get liberated and picked up by water. Rivers and streams carry them downstream, and because diamonds are both extraordinarily dense and completely resistant to chemical weathering, they travel without degrading. They accumulate wherever current speed drops, on the inside of a river bend, behind large boulders, in natural depressions on the riverbed, at the junction of tributary streams entering a larger river. These concentration points are the same places where gold accumulates in placer deposits, and experienced gold prospectors transitioning to diamond hunting have a significant advantage in reading river geography for this reason. The heaviest material always ends up in the same kinds of spots. The fourth environment is less commonly discussed outside professional geology circles, but genuinely significant. Eclogite is a dense, visually striking rock made primarily of large red garnet crystals and a vivid green pyroxene mineral called amphicite. Formed under extreme depth and pressure comparable to the conditions that create diamonds, eclogite represents actual mantle material that has been brought to the surface through various geological processes. When it appears in kimberlite pipes, it arrives as chunks called xenoliths, fragments of mantle rock dragged along by the eruption. Diamonds occasionally form as inclusions inside eclogite inclusions, locked within individual garnet or pyroxene crystals at the moment of their formation deep in the mantle. Some of the largest and most exceptional diamonds ever found, including several famous stones from South African mines, were trapped inside eclogite inclusions. In the field, eclogite is hard to overlook once you know what it is. The red garnets are often large, vivid, and almost gemmy in appearance, set against the dark green of the amphicite matrix. It's one of the most beautiful rocks in existence, honestly, and its presence in kimberlite material is a positive sign for the overall quality of the pipe. Knowing your craton context also helps you interpret negative results correctly. If you spend a day working river gravels in the right craton zone and find no pyrope garnet, no ilmenite, no chrome minerals at all, that tells you something useful. Either you're working a drainage that doesn't connect upstream to any kimberlite source, or the local geology simply hasn't been productive at that site. If, on the other hand, you find abundant pyrope and ilmenite with no diamonds, the source exists somewhere upstream. You're just working a section of the drainage that hasn't concentrated the stones yet, or you haven't processed enough material. Diamond prospecting at any scale is a statistics problem. The more favorable material you process in the right geological context, the higher the probability that one of those heavy grains is the one that matters.
Understanding the geology at a regional scale tells you whether an area is worth investigating. What you do once you're actually standing in the field is a different skill, one that comes down to recognizing indicator minerals grain by grain and reading the physical characteristics of anything unusual you find. The most reliable diamond indicator is pyrope garnet. Unlike the almandine garnet common in schists and gneisses across much of the Appalachian region, which tends to be dark, opaque, irregularly shaped, and relatively abundant, pyrope is a high-pressure mantle mineral. Its color is a vivid reddish-orange, often with a slight transparency that sets it apart from the dull surface of common garnet. Its density is noticeably higher. Picking up a pyrope grain and comparing its weight to a same-sized quartz grain makes the difference immediately obvious. In kimberlite-derived gravel concentrates, pyrope grains often have a smooth, slightly rounded surface from water transport, but retain their characteristic color intensity even after long travel distances. Geologists working diamond exploration regions in southern Africa and Canada use the chromium content of pyrope garnets as a proxy for proximity to the diamond source. High chromium pyropes tend to come from deeper, hotter source material and correlate more strongly with diamond presence. In the field, you can't measure chromium directly, but a pyrope with an unusually deep dark red to orange-red color, sometimes described as blood red or cranberry, is worth more attention than one with a paler, more brownish tone.
Ilmenite is an iron-titanium oxide appearing as dark gray to black grains with a dull, slightly metallic luster. It's common in kimberlite and appears consistently in alluvial concentrates from kimberlite source areas. The separation from magnetite is critical and simple. Hold a small neodymium magnet near your concentrate. Magnetite jumps to it. Ilmenite barely responds, if at all. Dark, dense grains that don't react to the magnet go into the keep pile for further examination. Chrome diopside is a bright, intensely saturated green pyroxene mineral, darker and more vivid than epidote, chlorite, or any common green mineral you'd expect to encounter in normal gravel. It grows under mantle conditions alongside diamonds and appears in kimberlite concentrates as a confirming indicator when found together with pyrope and ilmenite. Chrome spinel appears as small dark green to nearly black grains with an octahedral form, two tiny pyramids joined at the base, and exceptional density and hardness. Neither mineral is as widely recognized as pyrope garnet, but finding either in a concentrate alongside pyrope significantly strengthens the case for a kimberlite-derived source upstream. Olivine in alluvial gravel shows up as small, yellowish-green grains with a slightly glassy surface. Fresh olivine has a distinctly greasy feel that's recognizable once you've experienced it. When weathered, it turns brownish to orange and loses translucency, but its density still separates it from quartz and feldspar grains of comparable size. In kimberlite-derived material, olivine is typically the most abundant macroscopic mineral after feldspar, and its presence, especially when it's fresh enough to show the characteristic color and feel, is a useful broad indicator of the rock type that supplied the sediment. One thing that surprises almost everyone is that raw natural diamonds are rarely the colorless, brilliant stones seen in jewelry stores. Most diamonds found in their natural state, particularly in alluvial gravel, are some shade of yellow, brown, or gray. Truly colorless diamonds are the minority in any natural population. Yellow diamonds get their color from nitrogen impurities incorporated during crystal growth. Brown diamonds, which are extremely common in alluvial deposits and are sometimes called champagne or cognac diamonds in the market, get their color from structural deformation of the crystal lattice during or after formation. Gray diamonds often contain hydrogen impurities. Each rock environment tends to produce diamonds with slightly different color distributions. Kimberlite from deeper, hotter pipes tends to produce more Type 2A diamonds, stones with very low nitrogen content, often colorless or faintly pink or brown, because the extreme conditions during formation drove out impurities. Shallower, cooler kimberlites and lamproites more commonly produce yellow and brown stones. Alluvial deposits collect diamonds from multiple sources, so their color range is the broadest. You're essentially looking at the full spectrum of whatever the upstream geology has produced over millions of years of erosion. Rare natural colors include pink, blue, green, and orange, each caused by different mechanisms. Pink diamonds result from plastic deformation of the crystal structure, a structural distortion that occurs under specific stress conditions during formation or as the stone is transported upward. Blue diamonds contain trace amounts of boron, which is so rare in diamond formation environments that blue stones represent less than a fraction of 1% of all natural diamonds. Green diamonds owe their color to natural radiation exposure at or near the surface over geological time. Their color is often confined to a thin surface layer and doesn't extend through the entire stone. These fancy color diamonds can be worth dramatically more per carat than colorless equivalents of the same clarity and size. A fine blue diamond, for example, regularly sells for more than $1 million per carat at major auction houses. In the field, this color reality matters because many people scan gravel concentrates looking for something that resembles the polished diamonds they've seen in photographs: bright, flashy, colorless. A natural alluvial diamond is more likely to look like a small, pale yellow pebble, a slightly translucent brownish grain, or a dull-surfaced gray crystal with no particular visual drama. The luster, the density, the hardness, and the geometric shape are more reliable identifiers than color alone. Working alluvial gravel doesn't require specialized equipment. A basic pan or kitchen colander, a 5-gallon bucket, and a white tray for final examination will get you started. Focus on natural concentration points in the stream, inside bends, behind boulders, at tributary confluences, in depressions on the riverbed where current slows. Scoop gravel from these spots and wash it in stages, letting lighter material wash away while heavy minerals settle. The final concentrate should be examined in direct sunlight with a 10 times magnifying loupe, working grain by grain through the heaviest fraction. When something stands out, unusual weight, unexpected luster, any geometric crystal form, a scratch test on glass or quartz tells you if hardness is in the right range. Diamonds scratch everything, but corundum, topaz, and some garnets also scratch glass, so hardness alone doesn't close the case. Shape is the second test. The classic octahedral form, sometimes preserved even in water-worn alluvial stones, is a strong visual indicator. And the luster, that strong, almost wet-looking reflectivity on the surface of a raw diamond, different from the flatter, glassy look of quartz, is something that experienced prospectors describe as immediately recognizable once they've seen it under field conditions on a confirmed stone. Setting realistic visual expectations before you're in the field makes a significant difference in how you search. Most natural alluvial diamonds are small, under half a carat, often just a few millimeters across. Their color is almost never colorless. Pale yellow and light brown are by far the most common, followed by gray.
The surface of a water-worn alluvial diamond tends to be slightly etched or frosted from long exposure to water-ground chemistry, which reduces the immediate visual impact of the luster. But even through that surface frosting, the characteristic reflectivity comes through under direct sunlight, a brightness that doesn't quite match anything else of similar size in the concentrate. Triangular surface markings called trigons are another identifying feature unique to diamond. These are tiny, equilateral triangular etch pits that appear on natural crystal faces, formed by dissolution of the diamond surface during its geological history underground. Trigons are too small to see with the naked eye, but clearly visible under a 10 times loupe. Finding them on a suspected crystal is one of the strongest field indicators you can have. Quartz, zircon, topaz, and other diamond simulants do not develop trigons. This feature is exclusive to diamond and makes it one of the most definitive non-destructive checks available without laboratory equipment.
Professional diamond exploration in alluvial terrain doesn't just search for diamonds directly. It maps indicator mineral concentrations across a broad area to identify which drainage systems connect upstream to a productive source. By processing samples from multiple points and counting pyrope and ilmenite grains in each concentrate, geologists trace the source upstream through elimination. Higher counts in a left tributary than the right means the source is upstream to the left. Follow the gradient of increasing indicator mineral concentration and eventually you're pointing up the pipe. Before working any field site with the intention of collecting minerals, two things need to be confirmed: land access and mineral rights. On public land, national forests, Bureau of Land Management land, state parks with specific prospecting provisions like the Crater of Diamonds, the rules vary by location and must be checked in advance. On private land, explicit written permission from the landowner is essential. In the United States, mineral rights can be owned separately from surface rights, meaning that surface access permission doesn't automatically include permission to collect minerals. Most casual hobbyists collecting in small amounts for personal use falls well below any legally significant threshold, but researching specific regulations for your intended location before you go protects you from problems that are entirely avoidable. State geological surveys publish rockhound-specific guidance for most states, and several gem and mineral societies, including many local clubs affiliated with the American Federation of Mineralogical Societies, maintain resources for members who want to prospect legally and connect with experienced local prospectors who have already navigated access questions for specific sites. Finding something worth evaluating is the beginning of a process, not the end of one. What field knowledge gives you is the ability to recognize when that process is worth starting.
Now, what if you actually find something? A grain that's too heavy for its size, scratches quartz, shows that unusual luster, maybe even holds a geometric crystal form, but you genuinely can't tell what it is. That uncertainty is exactly where people lose money. Buyers who know more than you will pay far less than what a stone is worth, or simply tell you it's nothing, knowing you have no way to argue back. And that situation is far more common than most people realize, not because finding something valuable is frequent, but because when it does happen, the person holding the stone is usually the least prepared person in the room.
That's precisely what the Gemology Journey for Beginners training is for. Available in the first link in the description. You'll learn at-home identification methods for precious stones found in nature, hardness tests, density comparisons, luster and transparency evaluations using everyday objects, no professional equipment required. The kind of knowledge that lets you walk into any conversation about your find already knowing what you're holding. If you're not ready for that yet, no problem. Just subscribe and watch the next video already showing up on your screen. Every week there's new content on how to find, identify, and understand the real value of the stones nature hides in plain sight.
Thanks for liking and subscribing. Good luck, Gem Hunter.